So here's the scenario. You're living thousands of years ago and you're looking for patterns in triangles because triangles are a very fascinating shape and people have always been fascinated by them. And you might gravitate, in terms of looking for patterns anyway, you might gravitate towards a right angle triangle. Because as you can see here, I can very easily measure that this is 4 and this is 3 using the boxes. Now, they might not have boxes, and you could say for argument's sake that everything that I'm doing to this right triangle you could technically do to a normal one, but just for the simplicity of this scenario, let's just say you're focusing on right angle triangles, because they're just easier to work with when you have two kind of perpendicular sides you can change. And let's have a look at something interesting about this. So you notice that we have an angle, obviously, we have the side lengths and the angles, and this side length here is 4, and this side length here is 3. And you might notice, well, what would happen if I made this triangle bigger? Like I just made one of the sides longer, but I did the same to the other side. Well, let's say I doubled each side. So let's say I extend this side out to be 8 instead of 4. So here's 8, and I extend the other side out to be 3, or 6, sorry, instead of 3. So 3, 4, 5, 6. And then I finish off the triangle. What do we notice? We can see that the angle actually stays the same, but now all the side lengths have doubled. As you can see, obviously the two easily measurable ones have doubled, and then as a result the hypotenuse, as we call it, has also doubled. Or this side, I'm just calling it hypotenuse because you probably know what that means. The side opposite the right angle has also doubled. This is a right angle. So now we have 6, we have 8, and we have, well, if this one was called the hypotenuse h, this one is called 2h. Okay, and what we notice is that the sides can change as much as we want, but you can see the ratio, if the ratios between the sides are the same, so the simplest ratio is 3:4, and that's the same ratio as 6:8, you see that the angle is going to stay the same as well. So we see a very fundamental property about right triangles, that if we have sides in a certain ratio, the angle is always going to be the same. And if we know what one of those sides is, well, we can figure out what the other sides are just from using the same ratios. So I've written in the names of the sides here, and this is where you start doing a bit of thinking. So I'm not talking about where the name's coming from. I'm talking about where the ideas are coming from. So obviously the names are just random names. They don't actually affect the maths. It's just what we decide to call them. I could do another video on that. I want you to just go about the thinking of how this could have been invented. So let's just take one of the ratios, and for historical reasons that I won't go into, the ratio we looked at first, and there's a cool history behind it, but again, I don't want to go into it here because this is just about the thinking, is the ratio of the opposite side to the hypotenuse. And they decide to call that sine of, let's just say, the angle, okay? And obviously you might be thinking, oh, you're just telling us the information like in school. But this is where it's different. So let's say we know this ratio. Let's say we just have a table and we have all these ratios. We know that if the angle is this, we know what the ratio is going to be. We want to find out the ratios between the other sides, because obviously opposite and hypotenuse, what about this side? Or what if we don't know the opposite, but we do know the adjacent and the that kind of thing. We want to be able to see what other ways can we relate this, but we don't want to make a new ratio. We want to do that using this ratio that exists already. How could we do that? I want you to pause the video, have a think, draw out a triangle, mess around. Right now we have this side, the opposite of the angle, and the hypotenuse opposite the right angle. How could we get the adjacent side involved? You should pause the video and have a think about that. If you couldn't figure it out, I'm going to give you a hint, and I'm going to ask you to pause the video again. Think about the other angle in the triangle and what this could be equal to. So this angle here, I'll call it B. I want you to think about that other triangle and see what happens if we do the ratio with the angle B. But then obviously we don't know what the angle B is. We only know what the angle A is. Then can you maybe figure out what is the angle B in terms of the angle A? And then you can apply the ratio, and then that should give us this side. So I want you to pause it and just figure out the exact numbers with that kind of idea in mind. Okay, well, I'm going to hope that you paused the video and that you gave it a go. If not, again, I'd highly encourage that you do that. But I'm going to show you now what you could have come up with if you spent enough time thinking about it. Well, this angle here, we know this angle is 90, we know this angle is A, and we know all the angles have to add to 180 in a triangle. This is a theorem that's been known for a long time. So you have A plus 90, and I'll call this B still for now, plus B equals 180. And now when we solve for B here, or you could just use logic to figure it out, you'll figure out that it's actually equal to 90 minus A. Okay, so I'm going to write that in up here, this angle 90 minus A. And why the hell would we even bother looking at this angle anyway? Because now we can use the ratio for this angle. So with reference to this angle, I'm going to put this angle in green to make this very clear. In terms of this angle, what side is opposite of this angle? Well, now the opposite side is this side over here. The hypotenuse is still that, and this is the adjacent from the perspective of the green angle. So what can we write now? We can write that sine of 90 minus a equals, it's going to be, now I'm going to just call it adjacent, but it's the white adjacent, or the green opposite. Actually, no, I'll keep it all green. It's the green opposite side, though. So it's the other side, it's not the same one, over the hypotenuse, okay? Boom. Okay, cool. So now, if we know an angle A, and let's say we know the adjacent, and we want to know what's the ratio with the adjacent side, we know that, and we don't have to come up with a new ratio. We can use our ratio that exists already, and we can also use our angle that exists already. Perfect. However, people didn't really want to write down sine 90 minus a. They wanted a different symbol for it, and they were like, what could we call it? Well, two angles that add to 90 degrees are called complementary angles. And obviously, if this is 90, these two have to add to 90. And as you can see, a plus 90 minus a is 90. So if these two have to add to 90, they're complementary angles. So if we call this one the sine, why don't we call this one the complementary sine? Okay, let's call it the cosine for short. But cosine is short for complementary sine, because look, this is the complementary angle. So we can say that, I'm going to put this in yellow and white terms now. So we're thinking about the white angle now. We say that cos A equals adjacent over the hypotenuse. Okay, and that's our second one, and that's how you could have discovered it. Now we almost have every combination possible. We have opposite hypotenuse, we have adjacent hypotenuse. Now what if we didn't have the hypotenuse? I want you to see, using these two that we already know, can we come up with another one that relates the, can we kind of combine these two equations in some way so that if we don't know the hypotenuse, we can still figure out what the ratio is without getting a new angle or whatever. Still using our angle A, can we figure out what's the ratio between the opposite and the adjacent, just in case we don't have the hypotenuse side? I want to see if you can figure that out now. Pause the video, give it a go. We have these two equations. Try to find out what it would be if we don't know, or find an equation that doesn't have the hypotenuse in it. Okay, so we can do some very simple algebra here. Well, we can kind of treat these kind of like simultaneous equations. We can solve for the hypotenuse in one of these and just sub it into the other one. That's one way we can do it. Or we can think about the ratio between these two, and because they both have hypotenuse in them, they'll cancel out. They both technically do the same thing. I think as somebody who's done maths in school, you'll probably be more used to doing some kind of simultaneous equation. So if I solve for hype here, we can see that the hypotenuse is the opposite side over sine of A. Okay, and what we can do now is we can bring it down here, and we can replace this hype with opposite over sine A. So you have cos A equals adjacent over, and this is kind of confusing, so instead of saying over, I'm going to say divided by, just to make it easier. So I'm going to say adjacent over 1 divided by the hypotenuse, which is opposite over sine A. Okay, now what I can do is I can say that cos A equals, and then dividing by that is the same as multiplying by it, the fraction reversed upside down, sine A over opposite. And then obviously we wanted to figure out what the ratio is. So I'm going to bring the sine A down to the other side as a division. We get the cos A over sine A equals to adjacent over opposite. Okay, and boom, we just found out a ratio between the adjacent and the opposite. And you could call this whatever you want. Now, the modern kind of standard for maths is that we don't call this, well, we do call this something, but it's not one of the first ones we need to learn. People just decided, again, seemingly arbitrarily, again, the names don't matter, the specifics don't matter. The point is you could get all these numbers by yourself, but people, when they were giving names to it, they decided, and I'll do this in the next video, instead of giving the name to the ratio that we just found, they decided to give the name to this ratio here, the sine over the cos. I guess the reason being, because we started with the sine, we want that on top. And they decided to call this one, instead of writing A and A again, kind of like for cos, just mathematicians are a bit lazy. They didn't want to write sine 90 minus A. Same here. They decided to call that tan of A. And now we have three ratios, and well, we only started with one ratio. They're not actually three different ratios. We just started from the one ratio, and then we gave the other ones different names. And now, if we know any sides of the triangle, we can figure out, well, if we know any one of the sides and we know the ratio, we can figure out the other side. Or we can figure out a ratio using any two sides and use that to find information about the other sides. Very cool. And that's how you kind of, again, not how you could have discovered the names. The names don't really matter that much. The important thing is this is kind of where they come from, and this is how they were. Well, I guess this is a way that you could have discovered them yourself. And yeah, I think it's quite intuitive, and I hope that it was interesting. And I'll talk about the names in the next video or another video.